Today we're going to cover in section 2, we're going to determine how to figure out what the pH of something is. And then in the section that we'll cover tomorrow, we're going to learn how to titrate. It's where you exactly measure certain amounts of acids and bases to figure out uh, maybe how concentrated an unknown is or something like that. So today, though, we're going to cover acids and base indicators. So we're going to describe how they function. Um, and then in tomorrow, we're going to explain how to carry out an acid-base titration. And then from that titration, we'll be able to calculate the molarity of a solution that we don't know, its concentration, but we'll be able to figure it out from the data that we've gathered by doing a titration. So first thing we want to talk about are indicators. And indicators or acid-base indicators are compounds. They're usually organic dyes whose color happens to be sensitive to pH. Those of you that did the lab with the red cabbage has a dye in it, an organic compound that changes color depending on whether you put it into an acid, a base, or if it's in something that's neutral. So indicators change colors because they themselves are either a weak acid or a weak base. So this organic compound itself is a weak acid or a weak base. And here is the equation that is our model of how an indicator actually works. This example that we have right here is the one for a weak acid. We won't have one for a weak base. We're just going to use this model just for the weak acid. And notice that this weak acid begins with an H, and we know that according to Arrhenius's definition, anything that produces a hydrogen ion is an acid. So you can see this HIN, and the IN is the indicator anion, and so this indicator compound will ionize, and it will form a hydrogen ion, which we know in water will become hydronium ion, but here we're just going to focus for the moment on the hydrogen ion, and then we're going to have the indicator anion. The negative ion is the indicator. And so this is what happens in solution. Now the double-headed arrow is something that's important to notice. This is not something that completely ionizes. In fact, because it's a weak acid, it does not ionize completely, maybe only partially, might be at best. And the HIN and the IN are actually different colors. So in a solution that is predominantly HIN, in other words, there's way more of that than there is of the IN, it will exhibit the color of the HIN. If you put it into a solution where it produces more IN negative ions, then it will be a different color. So depending on whether I put them in an acid or a base, it will force those reactions either to be favored going to the right or favored as going to the left. So in an acid solution, any ions that are present, so we have, let's just begin with water, just pure water, and we put this indicator in there, and the indicator molecules have partially ionized to the hydrogen ion and the indicator ion on the right. If I now would add an acid to the solution, there is going to be an increase in the number of hydrogen ions because of the acid, and that means more of the hydrogen ions are going to, more of these hydrogen ions are going to react with the indicator ions to reform. They're going to go back this way. They're going to reform the original molecule, the indicator molecule. So they'll want to go to the left because I put more of these in it. And so that means there'll be more of these that can collide with these to reform this. So in this solution, this acidic solution, the ions are going to act like Bronsted bases, and they're going to accept the hydrogens, those protons, that this acid that I've just added has donated. And so there's going to be a lot more of these hydrogen ions, and they're going to latch on to those indicator ions and reform the original indicator molecule. So the indicator is going to be, the HIN is going to be present in larger amounts. And remember, what's ever on the left is not ionized, what's over on the right is ionized. And so whatever color that HIN is, that's what the color will be when I put an acid into it. See if you understand that. Because I'm going to have a lot more HIN than I will have IN ions, indicator ions, then that's whatever I have the more of is going to be the color of the solution at that moment. Now, if I were to put it into a basic solution, and remember, according to Arrhenius's definition, we're going to use that for right now as far as the ones that produce the OH negative, the hydroxide ion. These hydroxide ions are going to combine with the hydrogen ions, and they're going to make water. They're going to make water. And that's going to cause more of the HIN, the indicator ions, to further ionize to offset that loss of hydrogen ions. So there's going to be more of it will ionize to replace those hydrogen ions that combine with the hydroxide ions to form water. So these indicator molecules are going to further ionize, and we're going to end up with still more indicator ions. And the indicator ions are going to be now in larger numbers, and so the color is going to be the color of the indicator ion. Whatever color the indicator ion is, that's the color that the base will be. So you can see if I put the acid in there, the acid increased the hydrogen ions, and that caused more of those to combine with the indicator ions to reform the original indicator molecule. And so we'll have more molecules than indicator ions, and so it will be the acid color. In this situation here, in a basic solution, the OHs will snag up a lot of those hydrogen ions, making water, and so the indicator molecules, what's on the left, well, more of those will begin to break apart to replace the hydrogen ions that have been used up by the OH to form water, and that will just add 2 more indicator ions. And so now I'm going to have a larger number of indicator ions, and that color is going to show. Now, to measure the pH of something, we're going to often use meters to do that, but the purpose of an indicator chemical and its color changes helps us to figure out kind of what part of the range we're in. So the pH range over which an indicator changes color is called its transition interval. So if it's one color, let's say I put a little bit of acid in there and it's the color of the indicator molecule, and now I start adding hydroxides to it, a base to it, the molecules, remember, are going to start breaking apart to replace the hydrogen ions that got used up by the base, and I'll have more of the indicator ions and it'll change colors. So, but it doesn't happen instantly. It's just not like one instant it's one color and the next instant it's the next color. There's actually a transition from one color to the other. It does usually happen fairly quickly over a narrow pH range, but that's called a transition interval. Now, a pH meter, its job is to measure the pH directly by measuring actually the voltage between two electrodes. So they have two electrodes that usually have a battery attached to it, and it goes to a meter that measures the voltage, but instead of measuring in volts, they have a scale written on there that goes for pH. And the voltage changes as the hydronium ion concentration changes. So in the indicator model, we have the hydrogen ion. So the greater the hydrogen ion is, the greater the voltage. The lower the hydrogen ion concentration, the lower the voltage. So we measure pH more precisely with a pH meter than we can with the indicators. So when you did the cabbage, you kind of got a range for each substance that you tested. You gave it over a range. Same thing here. Any indicator that we're talking about here would do the same thing. But a pH meter can give it, depending on the quality of the pH meter, can give it like to the nearest tenth or hundredth of a pH. Now, the range, these indicators are often, the type of indicator you use depends on what you're combining. So if you look at over on the left, if you're combining a strong acid with a strong base, if you're putting those two together and you want to find out when I have like exactly used both of them up, then I'll want to have an indicator of one of these two that is chosen right here. Since this is a strong acid and a strong base, methyl blue will change from pink to yellow in the range of about, as it says, 4.4 to about 6.2. In that range, the color is going to go from pink to less pink, a little more yellow, to kind of like it by the time it gets to about neutral. Maybe it's well, when it gets about in the middle, it's probably going to be somewhere around 5, I'm guessing. And then when it gets over the base side, then it'll be yellow. Bromethymol blue, a different indicator, in an acid, it's going to be yellow. And then its transition from an acid color to a base color, let's say it started out acid and I keep adding bases until it's used up all the acid, and now I have too much base, it'll eventually become blue. But you can see in the middle there's kind of a greenish blue or bluish green, however you want to describe that. But the transition for that one, where the color changes, is around from about 6.2 to about 7.6. Now we could have another combination of chemicals, acids and bases that we're putting together, and this is going from a strong acid to a weak base being added together. So it'd be like hydrochloric acid, and then maybe we're adding like ammonia to it. The best indicator for this type of a chemical reaction is methyl orange, and its transition range is from 3.1 to 4.4, where it will change from red to yellow, and in between it's kind of orangey, kind of in the middle part of that range. Bromphenol blue starts out yellow at anything less than a pH of 3, and by the time it's greater than a pH of about 4.6, it's that pinkish purple that you see on the right, and in between is kind of that pale pink, and its transition is 3.0 to 4.6. Now, if you have a weak acid and a strong base, the indicator of choice often here, the one that we often use at school, is called phenolphthalein. It has a lot of consonants in the middle, and we don't really pronounce the pH in the middle. It's like phenolphthalein. And the transition here is on the base side between 8 and 10 is where the color will change. Now, in an acid, it's clear. When it's going through the transition, it will change from clear to a really faint pink to a darker pink, and by the time you get to about a pH of 10, it's a nice bright pink as you see on the right. But the transition is around from 8 to 10 is where the color will change. Another one that they sometimes use is called phenol red, and its transition is from 6.4 to 8.0. So which indicator you use kind of depends on how strong or how weak the acid is and how strong or how weak the base is.